So we are going to continue with our small signal analysis, okay, of the 741. So what did we do last time? So we started off looking at the input stage. So we decided to split. So we had three stages. One is the input stage, differential is single-ended. Second stage was the common emitter, which gives you a lot of gain. Third stage was the output stage, which drives power, right, which can drive a lot of power, very small loads. So for each one of these, we want to create an equivalent circuit and then use that to calculate the overall gain and so on, input impedance, output impedance, whatever you want. Okay. So we started off with the input stage, and we did we made a few assumptions. We assumed that Ry was much less than Rx. So you can actually go ahead and replace the current mirror with something close to a ground, right? At least as far as calculating the GM, the transconductance, right? So we just have the Q1, Q2, Q3, Q4, this quad, transistor quad, right? And we want to calculate IC3 and IC4. What is the overall, if you assume these are the directions for IC3 and IC4, what is the overall I out? It's just 2 IC3, right? Direction we'll need to see, but this is 2 IC3. And I think last class you did the analysis. You analyzed this very simple equivalent circuit for the transistors, and you found that the first of all, you found out number of things. First of all, you found out, if I'm not mistaken, is this right? Oh, sorry, VID by 4. Is this right? Do you remember this? So you have VID by 2. It splits equally between the PNP and the NPN. Correct? So therefore, what is your GM1? What is your overall transconductance, effective transconductance of the input stage? GM1 by 2. What is the value? What is the value of GM1 by 2? So approximately 180 microsiemens. Okay. What is the input impedance? Differential input impedance? Anybody? What do you need to do to calculate input impedance? You need to calculate this current. Can you find out what that current is? What is it? V1 by R by 1. Okay. So can you calculate what it is? You already know V1, right? Okay. So what is our input impedance here? What is the input impedance here? For this equivalent circuit? You have basically calculated I1. So here it is, because the voltages divide equally, right? The input impedance will just be 2 R by 1 for this circuit. If you take the overall RID, it will be 4 R by 1. Correct? What is this? Can somebody calculate? we're going to assume beta naught is 250. Okay. So what is the value of 4R pi 1? How do you calculate R pi? Beta by GM, right? Okay, so what is value of 4R pi 1? GM is IC by VT, right? 2.72. Okay. Okay, 2.72 mega ohms. Next step is to calculate output impedance. Okay. So to calculate output impedance, you go back here. So it will be this output impedance in parallel with this output impedance. What is the output impedance looking down into such a circuit? What is R down? I'm going to call this ROD. Well, what is this? GM6 into RO6 into 1 kilo ohm. Is that right? Do you remember the exact expression? So for a cascode, normally we use GM, GMR of the gain of the cascode times the resistance at the bottom. Does anybody remember the accurate expression for that? Okay, let's do a quick exercise in a few minutes. Can you calculate this? Take a bipolar. I have an R here. This is Vn. Okay, I want you to calculate. Okay, so you can even ground this. I want you to calculate accurately the value of R out. Don't make any assumptions. Don't neglect anything. R into plus R into R naught. This is what you're getting? Have you neglected R pi? Okay, capital R is, in this case is, so okay, so let me call this R prime. Is this right? Is that what you're saying? Is that right? Doesn't seem right. So you're saying it's this? Yeah, so that's exactly what they're saying. Okay. So this is the accurate expression. Okay. So the reason I want you to do this is because, so if I say this, it's 1 plus. If I assume that RO is much larger than R, let's assume for now that it is true. Okay? Because R parallel R pi will be some number which will be less than R, and if R out is much larger than that, we can assume we can neglect definitely this first R prime term. So the reason I asked you to calculate this out is it's actually R out into 1 plus GM R prime. So normally what we have been doing is we have been neglecting that one term. Okay? Here we are going to see a case where it is not necessarily negligible. Okay? Why am I saying that? Can you calculate RO up and RO down? So RO down is straightforward. You already know R. You know R pi, calculate it. Right? How do you calculate R up? RO up? It's actually the same configuration. Right? You're looking into the collector of this PNP. What resistance do you have here at the emitter? You have 1 over GM of Q2. Right? And it so turns out that GM of Q2 and GM of Q4 are equal because they carry the same collector current. Right? So calculate RO up, RO down and the overall R out. If you want, you don't even need to neglect R prime. Just calculate the completely. Right? Don't even neglect R prime for now. Go back to which one? The overall circuit diagram? The schematic, right? Okay. There you go. I can already tell you what RO up is going to be approximately. Because we just looked at what is GM. So we looked at what happens when you have a resistance R here. What is that R here? It's 1 over GM. Right? So what is GMR? 1. So the resistance looking up is most probably going to be 2 R out. Right? Is that right? Okay, what is the resistance looking down? In this case it's more straightforward. So just calculate the overall R out. Good question. Keep track of which R out you're changing, right? Keep track of whether it's RO4 or RO2 because Q6 is an NPN, Q4 is a PNP. I'll give you the VA numbers. Assume that the early voltage is 130 volts for your NPN and 52 volts for your PNP. You get something like this. On one side you have 2 RO4. On the other side you have 1.4 RO6. 1.4, is that right? So you calculate the 1 plus GM R prime and so on. Is this right? 1.4 approximately, like 1.3 or 1.4. 1.36, huh? What do you get? Okay. So what is this value? What is RO4, what is RO6, and what is the overall output impedance? How much is it? Is that right? 7.8? 7. I think it should be closer to 7. Okay. Okay. So I guess we waited for some time. So why don't you go ahead and try it out in your at home? Okay. But it ends up being around 7 mega ohms. Okay. So we have got the equivalent circuit for the first stage. So what is the input impedance? 2.7. And what is the GM? 180 microsiemens. GM1. Okay. GM1 times DID. So this is the equivalent circuit for the first stage. So let's go ahead and find out what happens in the second stage. What did we have in the second stage? We had some bias voltage there. This is this is what we had. This is what we had in the second stage. Correct? What is Q13B? That is at 550 microamp bias current. Remember, we had a split collector. Right? We had 550 microamps, so I have just called the Q13B. Q13A goes to the output stage. Right? Okay? So let's do one thing. Let's calculate Rn. So I'll call that Ri2. What is Ri2? How do you calculate Ri2? To do that, you need to know what is input resistance at the base of 17. What is that? What is that? What is the input resistance here? Huh? Louder, sorry. GM17, okay. R0 17 into 100 ohm. R pi 17. So you're taking GM17 into R pi 17 into, is that right? What is GM17 into R pi 17? It is just beta of the transistor, right? Okay. So you're telling me it is beta of the transistor times 100 ohms. Is that right? Huh? Exactly. Right? You're going to get beta naught plus 1 times 100 plus R pi. That will be the input impedance. Everybody remembers this from your bipolar. You have a degeneration resistance. Input resistance is R pi plus beta naught plus 1 times Re, where Re is the emitter resistance. Right? Okay, calculate that. What is that? The bias current is 550 microamps. Calculate what that is. Let's keep that in mind. $37 kilo? Yeah, correct. Okay? $37 kilo ohms. You got it. Okay. 37 kilo ohms. Okay. So now what is Ri2? Nothing but R pi 16 plus correct? Yeah, we always do that, right? When calculating input impedance, we always neglect RO. When calculating transconductance, we always neglect RO. Right? Only when calculating output impedance, we take into account RO. $16.2 microamps is the bias current of Q16. What is it? 5.7. Okay. 5.7 mega ohms. You are okay. So Ri2 is done. What next? Transconductance. What is the transconductance? GM2. So let us say you short this, find out I out. What do you expect it to be? You don't need to short it and calculate it and so on. You can look at it and tell. GM2. Can you check again? Is it really going to be GM2? Okay, first of all, what is the gain of Q16? Almost 1, right? Typically it will be output impedance is 1 over GM. This impedance is quite large. It's the 50K in parallel with 57K. 1 over GM will be in like few tens of ohms, probably maximum few hundreds of ohms. Okay? So definitely the gain of this is going to be very close to 1. So you can neglect this. So V in directly appears at this point. What is the transconductance of this? We have done this before even in MOSFETs. It is GM17 over 1 plus GM17 times 100 ohms. Right? What is this? Can somebody calculate this? What is it? 6.8 millisiemens. Okay. Okay. What is R out? Next I am going to calculate R out. What is R out? It's R out of Q13, RO13 in parallel with, right, RO17 into 1 plus GM into 100, GM17 into 100. Can you calculate that? What is it? 80? 82 meg kilo ohms. Okay. Is that right? Somebody said 82 kilo ohms. 83. 83.8. 83.8? Okay. So I'll just call it 83. Okay? You got it? You will get it. Okay. So now we also have the equivalent circuit of the second stage. Okay, and this happens to be 6.8. Correct? Okay. How about the last stage? So let me redraw it. So this is Q19, this is Q20. Okay? Okay? So now how do you find out Ri, Gm and Ro and so on of this stage? Maybe instead of finding Gm, now that you have a load resistance, maybe it's easier to calculate just the voltage gain. The output stage, instead of having it as Gm in parallel with a resistance, it may be easier to do it as a voltage source in series with an output resistance, where the output resistance should be very small, right? That's what you're trying to achieve. What is that voltage gain going to be? It's going to be very close to 1. That is what you want, right? Because this is like an emitter follower on either side. Okay. Now to calculate the input impedance, you need to know what RL is first of all. Okay. Second thing, you also need to make certain assumptions, like how much current is flowing through Q. Actually, did we discuss that? How much current is flowing through Q14? Can you check if we discussed it? We did. What is the bias current of Q14? 142 microamps. 152 microamps. Okay. So in reality, if you want to calculate, you need to know what RL is. Okay. And you really need to know size. So in class we assume 3 times, but it actually depends on how many times you are going to make this. Just for ease of calculations, we did 3 times. Okay. So in reality, the bias current may be much more because you may want to drive very large loads, right? So we'll make some certain assumptions. So let's start off making some assumptions. Okay. So we'll start off assuming, let's say 2 milliamps. But okay, just remember that for the last stage alone, it will depend on the load, right? And details. We'll assume RL is 2 kilo ohms. Okay? Now what happens is, let us say you have a signal Vi3. Okay? The way this output stage works, we'll discuss it after once we get to output stages, we'll discuss it. But the way this thing works, for now just take it, okay? we'll assume that only once, only Q14 is on and Q20 is completely off. That's what we'll assume right now. Okay, you'll learn the reasons for this later. Okay, so Q20 will be completely off. You have Q14 and RL. So now you can find out what your input impedance is at the base of 14. Then you can find out the resistance of these diodes. You can find out the resistance of this, right? And then, so therefore, you have all those resistances at the emitter of this transistor. What is the number of this transistor? I forget. Can somebody tell me the number? 23. Okay, right? You can find out the overall input impedance. You can find out the overall voltage gain is 1. How do you find out the output impedance? So to find out the output impedance, a first order would be 1 over Gm, but of course, since you have finite beta here, you can find out what the impedance is looking out here. Okay, you can calculate what the output impedance is. Why don't I leave that as I want you to calculate and tell me next class, beginning of next class, I want you to calculate and tell me what assuming these 2 milliamps, 2 kilo ohms, assume that Q20 is off, find out what RI3 is, find out what RO3 is. Okay, we have already done it for the first two stages. There's no big difference for this particular stage. Okay, or maybe better is if I actually give you the number, huh? Before that, let's of course assume 250. What else do you need? 2 milliamps, 2 kilo ohms. Yeah, I think once you assume these, you have all you need to know to calculate. Need the the betas. So these are the numbers you should be getting. Let me just give them to you. Why don't you cross check them? Okay. These are the numbers you should be getting. Okay, I want you to cross check them. Okay, so this is the equivalent circuit for the third stage. We call this AV3. Can you calculate the overall voltage gain, AV? Now that you know the equivalent circuit for all the stages, calculate the overall voltage gain of the op-amp. What is the overall voltage gain? This is the voltage gain of the first stage. Voltage gain of the second stage. Voltage gain of the third stage. Correct? Can somebody calculate this? These two numbers? What is it? Sorry? 3.2 into 10 raised to 5. That is the overall. That is correct. Okay, can you tell me what the gains of the first stage, second stage and third stage are? First stage is what? 5? 565. That is the first stage? Okay. 565? Okay, what about the second stage? 559. Okay. What is this? 3.2? Okay. So the voltage gain is some 3.2 to 10 power 5 volts per volt. Right? Pretty large. One last thing we didn't talk about was compensation. So where would you, if you had to do compensation for this, where would you put the compensation capacitance? So you have the first stage here. Okay. Give me a second. Yeah, so you have the first stage here. You have the okay, sorry, where is the second stage? Missing the second stage. This is the second stage, right? This is the third stage, right? You have three stages. Where would you put the, if you needed to compensate this op-amp, where would you put the compensation capacitance? Huh? Second stage. Where would you put it in the second stage? So let's look at the second stage. You're saying between the gate and, sorry, you mean the base and collector of Q17? Is that right? You want to compensate using small values, or you don't want to do that? Correct. So what does that mean? You want to use the same technique which you use, which is Miller multiplication. Correct? So the most natural way is to put it across this, case where you have a lot of the common emitter stage. Correct? But then people usually put it in here, okay? Because the emitter follower also has a gain of 1. Okay? So normally it's compensated between these 2 points. So you see the basic ideas, techniques, from the higher level, very similar. Except you've added an extra stage, right? Which is to drive, because it happens to be a general purpose op-amp, to drive very large loads. Okay, so let's stop here. And so tomorrow, right, if I'm starting from tomorrow's class, maybe for, maybe for 3 or 4 classes, we'll go back to MOS op-amps, but we'll study, so we have pretty much done all the, main kinds of op-amps. But one thing we have not studied are differential op-amps. That is when you have differential inputs and differential outputs. Okay? There are some special things you have to take care of. The basic structure will be very similar, right? What is the difference between having a differential output and a single-ended output? Actually nothing much, right? Instead of having a current mirror there, you would just put in two current sources instead of current mirrors. Now that you have a differential case, you need to make sure that the common mode voltages are the same on both the outputs, because you want a purely differential output. So the two sides need to be completely symmetric now for DC and AC.